good morning, good afternoon, good evening, depending in which part of the world you are. But I hope you're still all on the 13th of April, so that I can wish you all a happy World Quantum Day. Yeah, in our colloquium this morning that we've organized together with various other African countries, and you see our representative, Professor Mourad Telmini from Tunisia, with us, and I hope that others will join us just now. We are very fortunate to have Professor Barry Sanders as a speaker. Barry is the director of the Institute for Quantum Science and Technology at the University of Calgary, and he's also the lead investigator of the Alberta Innovation Fund project on quantum technology. He's also a distinguished professor at University of Science and Technology in China, and a visiting faculty member of the Raman Research Institute in India. Yeah? Barry started his academic career at University of Calgary back in 1984, where he did his BSc, and then he completed his, at that time, I think it was a diploma, but probably today we would call it a master's, at Imperial College, working with Professor Sir Thomas Kibble. And he did his PhD also at Imperial College with Sir Peter Knight. Yeah? And recently he published a very, very interesting paper on observing a changing Hilbert space in a product. And he will speak about that today. So Barry, without further ado, people are here to listen to you, not to me. So if you would like to start your presentation, you're most and welcome. Thank you very much for joining us today. Yeah.
Thanks very much. Thank you, Francesco. Thank you, Mourad, for giving me a chance to speak about this topic. Yes, I'll talk to you about observing a changing Hilbert space inner product. You can see on this slide that the work was published in January. You can't see it was January, but it's published in January in the Journal of Physical Review Research. And before I go to the next slide, let me just give you an idea of what the question is. So, you know, quantum mechanics involves states that we represent as vectors in Hilbert space. And Hilbert space is a complete inner product space. And the question I had was, what happens if the inner product changes? So the way I like to put it is, suppose you wake up in the morning and Hilbert space has one inner product. And by the time you go to sleep at night, the inner product's changed. Is that allowed? Would you observe that change? So this is really the question. And inner product is really about two properties. One is the norm of the state, and the other is the angle. And so if your inner product changed, then the norm of the state might go up or down, and the inner product between states, or the angle, can change. And that means that when you wake up in the morning, two states could be orthogonal, and by the time you go to sleep, they'd be non-orthogonal. So is that allowed? And if it's allowed, can it be observed? And that's really the issue that we're going to consider here. And I'll answer all that. So first, I'll just tell you the table of contents. I'll go through the introduction to the topic, give you background on who did what in this field. I'll tell you about our approach to dealing with it, then convey the results, and then finish with the conclusions. On the right, you can see a picture of Calgary. I'm actually in Sydney, Australia at the moment, but that's my home city. And then down here, you can see I like social media, so I'm reachable various ways. Okay, this slide is telling you the context for our work and the aim. So I want to go through this slowly, make sure that the idea is clear. So let's talk about the inner product in quantum mechanics. As I said before, the idea is in quantum mechanics, we learned that the states are rays or vectors in Hilbert space, and Hilbert space is a complete inner product space. So the way that I like to represent it, I'm going to use the script H to refer symbolically to Hilbert space. And the way I think about Hilbert space is it's a pair. So the script V is a vector space, and the script I is the inner product on that vector space. So it's a vector space and it has an inner product. And then the complete property is just things that there's a Cauchy sequence of vectors closes in the space. I'm not going to worry about that. We don't need to worry about that property, but the inner product's important. Then the idea is that that Hilbert space, that's a pair comprising a vector space and inner product, the inner product just takes a Cartesian product of the vector space with itself and maps it to a complex number. So if we take ket phi and ket psi, we have a rule for turning ket phi into bra phi, and then this has meaning to us. And so if ket psi is a column vector of complex numbers, ket phi is a column vector of complex numbers, we turn the column vector of complex numbers to a row of numbers that are complex conjugate, and then we do the standard inner product between the row vector and the column vector. And I'll call the row vector, I'll call it a covector. So it's a row vector of complex conjugates. So this is out of undergraduate quantum mechanics. And the question I asked at the beginning is, what if this inner product were to change during the day, from the time you wake up to the time you went to sleep? And when I ask that question, I'm thinking that you prepare a state in the morning and then you measure in the evening. Would something be different? And so in this way of thinking, and I'll make it a little more clear mathematically, I like to think about ket psi as a description of preparation. So in the morning, you get up, have breakfast, prepare a state. Well, ket psi, that is just a description of how you prepare. You know, you can take an electron and make it spin up by putting it in a magnetic field, and you know, there's different ways to do it, but that's really what a ket psi is a description. Then the bra phi, I like to think about as the description of the measurement. So before you go to sleep, you decide to measure the state. The bra phi is the measurement. And then the inner product between the two is a complex number. So it's the complex probability amplitude for your measurement outcome. So you prepared psi in the morning, you measure phi in the evening, and then that complex number tells you that's what the inner product means physically. And so I'll tell you about what happens if the inner product changes, and that's not been done before. So the work that I'm telling you is surprisingly the first time that the question's been posed and answered. Okay, so the aim of this work then is to establish, and the idea is to make a framework. So to make sure that we get rigorous, the idea that the inner product on Hilbert space can change. And we expect this and ensure that we do it in a way that's consistent with quantum mechanics. And so the idea is, I'm claiming that we can show that the inner product can change from morning to evening. I'm going to claim that it's observable, and I'm going to claim that I'm not breaking any rules of quantum mechanics in doing that. Okay, so now I'll tell you, I'm going to motivate the work and tell you why it's important. And for this, I'll give you some background on what other people did. So is the changing inner product consistent with quantum mechanics? You know, so I'm claiming we can change it and it's consistent. Is it so? Well, first of all, there's some work that was done that says quantum mechanics is consistent for inner product choices. So the way I like to think about it, suppose that I live in a universe where Hilbert space has one inner product, and you live in a universe where Hilbert space has different inner product, but it doesn't change. Would quantum mechanics be different? And the answer is no. That if I live in a universe with one inner product, you live in a universe with another inner product, no change in the inner product, it doesn't matter. And this is intuitively what experts in quantum mechanics expect. Like you say to them, you go to an expert and you say, you know, Hilbert space doesn't have to have a unique inner product. And an expert says, okay, but you choose one and then everything will be consistent. It's essentially related to a basis choice. And so this idea that the inner product doesn't change is actually exploited. There's a giant field of research. You know, it's hard to go to a journal like, say, Nature Physics, where there's, you know, you see lots of articles on PT-symmetric Hamiltonians for this or that. And the idea is, and I'll go into this more during my presentation, but the idea of the PT-symmetric quantum physics, the idea of quasi-Hermitian Hamiltonians, and so on, are just another language. Those are other languages for talking about a choice of inner product, as I'll explain. But observing a changing inner product has not yet been addressed. So this is what we'll do today. You'll see what happens. Now, people have studied the question of whether a choice of inner product can be an advantage. And I won't go through, literature is sometimes misleading about this. Some people made claims that don't stand the test of time. These are good works. I'm not claiming otherwise. So can it be advantageous? Well, one would be, if you wake up in the morning and two states are not orthogonal, in the evening they are orthogonal, you might have a way of measuring non-orthogonal states, and therefore you might perform quantum cloning. And then this paper, you can see I'm in there, and it's in the group of Shui at the Beijing Computational Science Center. So the work shows how to do quantum cloning where we simulate experimentally an inner product change. And on computation, you can ask the following question. You can say, if the inner product were to be different, would that change complexity classes in quantum computing? So there's all kinds of questions you can ask if the inner product could be different or could be changing. And the idea here is I'm going to show you that the idea of a changed inner product is completely equivalent to the question of exact PT symmetry. And I'll go into it, but I'll just point out to you that the PT symmetry I talk about is not necessarily parity time or point reflection time. It's a generalization of that. And I'll explain what PT can mean generally. So the particle physics idea of PT is a special case. And so the idea that this is known before my work, that if you had two universes with two different inner products of Hilbert space, and you're treating closed systems, then there's no way to distinguish between those, which quantum mechanics applies in which universe. So you can't measure which inner product you've got. But in fact, the idea of distinguishing between inner products in an open quantum system was not touched. Okay, so that gives you some background. And then here's our claims and what's novel. So I'm going to make 4 claims here. Number one, that we've introduced a framework that's consistent with quantum mechanics for changing the Hilbert space inner product. Number 2, I'll claim that changing the inner product is expressible as a quantum operation. Specifically, it'll be a completely positive channel that's not trace preserving. Number 3, that the framework will show how this framework for a changing inner product relates to open PT-symmetric quantum dynamics. And the final one of the 4 claims is that we have a unitary qutrit protocol to simulate the inner product change of a qubit. And I'm currently collaborating with an experimental group on implementing this simulated change of inner product. Our approach is different from what others did before in inner product in a few ways. Number one, in order to get the mathematics right for a changing inner product, we employ a Cstar algebra to do it. So, it's a very formal mathematical physics way of doing quantum mechanics, but by bringing in Cstar algebra, it ensures that we don't make any mistakes. Everything has to be done right, and it's checkable. Number 2, we employ the freedom in Hilbert space representation to construct that quantum operation. So the representation that's chosen with Hilbert space is not physical, so we choose a convenient representation to make this simple. Number 3, as a byproduct, we've operationalized PT symmetry via the inner product change. So PT symmetry, as I mentioned, is extremely well studied with experiments appearing in some of the best physics journals there are. And when I say operationalize, what I mean it in the sense of operational quantum mechanics. Bush, Lottie, and I forget the third author, but there's a book on operational quantum mechanics. So I'm using their definition of operational. Okay, so there are many papers on PT symmetry, and I'm telling you that closed PT symmetric systems are equivalent to inner product change. So in this slide, I just want to bring to you some papers in PT symmetry that give you a flavor of the field. So back in 1998, Bender and Bocher had a paper out in Physical Review Letters called Real Spectra in Non-Hermitian Hamiltonians Having PT Symmetry. So this is the seminal paper in the field about PT symmetry. And this paper essentially says, so, when we do quantum mechanics, we say that the Hamiltonian has to be Hermitian or self-adjoint. And these guys said, no, you can have a consistent quantum mechanics with a non-Hermitian Hamiltonian, provided that it satisfies PT symmetry. And the PT symmetry is motivated by the particle physics PT symmetry, but it's more general, where P is, all we need to say is that P is a unitary linear transformation and T is an anti-linear transformation. And if the Hamiltonian commutes with any P and T operators that are respectively linear and anti-linear, then quantum mechanics is consistent. Okay, so that's the seminal paper. A few years later, there was a very nice paper by Mostafazadeh, and he essentially proved, like this paper says, that a non-Hermitian Hamiltonian with PT symmetry will have real spectra. More carefully, it's real spectra with the lower bound, so it's semi-bounded. Mostafazadeh then said he proved that exact PT symmetry is equivalent to hermiticity. So what Mostafazadeh said is, it's not necessarily the case you say a non-Hermitian Hamiltonian having PT symmetry, but what Mostafazadeh showed is that if you're careful with how you treat the inner product, then if a Hamiltonian has exact PT symmetry, i.e. the Hamiltonian commutes with PT, then it is Hermitian. So Mostafazadeh's paper is essentially saying that you need to be careful what you call Hermitian. And if you're careful and do it properly, then exact PT symmetry is just redefining hermiticity. Then it was later that Brody wrote a paper which is called Consistency of PT-symmetric Quantum Mechanics. So Brody proved, it's like Mostafazadeh is saying if it's exact PT symmetry, then the Hamiltonian is Hermitian. You just have to be smarter about what you call Hermitian. And then Brody is saying that's absolutely consistent with PT-symmetric quantum mechanics. So Brody's paper proves that PT symmetry is just about inner product, the hermiticity, and that it is quantum mechanics. And so that's what I said before. If you live in a universe with one inner product, I live in another, then our quantum mechanics are the same. So a different inner product in two different universes would not lead to any different physics. That's what they're showing. And again, the question I'm asking is, what if it changed in your universe? You wake up in the morning, and then by the time you go to sleep, it changes. Will that be consistent? And is it observable? So that wasn't addressed in these papers or subsequent papers. And then this is the paper I was on with Shui's group, where we did experimental quantum cloning in a pseudo-unitary system. And so this paper, what we were concerned about was we engineered a change of inner product so that we were able to do quantum cloning. And we could, if the states are not orthogonal, and then we engineer it so it becomes orthogonal later on, we are able to do perfect cloning. The problem is when the inner product changes, the norm can change. And it turns out that when we do so, we're able to clone non-orthogonal states this way, but we lose enough copies that our cloning is completely equivalent to non-deterministic cloning protocols. So we know in quantum mechanics, cloning is not possible, but it is possible to clone perfectly some of the time and lose the rest. And so our change of inner product is completely consistent with non-deterministic perfect quantum cloning protocols. Okay, so that gives you some flavor of the field, but there's hundreds or thousands of papers in this field that you'd need to look at to get a full picture. Now I want to explain to you the mathematics of PT symmetry. So let's go back to this slide. We have these papers. I want to tell you what it means to have PT symmetry. And so first of all, as I said, that P in particle physics would be point reflection symmetry, or often called parity symmetry. T is the time reversal symmetry, but we just generalize it. All we care is that P is a linear isometry. So an isometry on Hilbert-space is what we call a unitary operator, and it's linear. And T is antilinear. And so it's an isometry. And the antilinearity just says if you have A times one state plus B times another state, then A becomes A star, the complex conjugate, B becomes the B star. And so it's just a unitary transformation of the first state times A star and the second state times B star. And P squared has to be the identity. So applying the linear isometry twice brings you back to where you started. And applying the antilinear isometry twice also takes you back to where you started. And P and T are commuting. They commute with each other. So if for any operators P and T that satisfy these properties, that's what we call P and T. And it could be point reflection symmetry and time reversal, doesn't have to be. Then a Hamiltonian is said to be PT-symmetric if the Hamiltonian commutes with PT for any of given PT. So if you make up any P and T satisfying these conditions, and then you have any H such that it commutes with PT for any given P and T, then that's a PT-symmetric Hamiltonian. And it doesn't have to be a Hermitian in the given basis. So that's enough. And then this is what Mostafazadeh and then Brody essentially show that is just redefining hermiticity. If there's exact PT symmetry, then H and PT don't just commute, but they share all eigenvectors. So in the literature, when they talk about exact PT symmetry, that's what they're saying, that H and the product of P and T share eigenvectors, and that implies that the Hamiltonian possesses the real eigenspectrum. And that's the point of this seminal paper by Bender and Bocher is this having PT symmetry just comes by saying if you impose shared eigenvectors between H and PT, H has to possess the real eigenspectrum, and it's got a lower bound. And then Mostafazadeh's work is saying that that's equivalent to hermiticity. And what he's saying, what Mostafazadeh says, he proves it for the finite dimensional Hilbert-space case. So Hermitian is well defined here. So if the Hamiltonian is finite dimensional and diagonalizable with exact PT-symmetric property, then there's a positive definite metric operator eta such that eta inverse H dagger, so H dagger is the adjoint in the usual sense, then eta inverse H dagger eta is equal to H. And so I said before that with what Mostafazadeh is telling us is, in the PT-symmetric Hamiltonian is Hermitian, but you have to be careful how you define Hermitian. So this expression shows you how to be careful. That, in regular quantum mechanics, we would say that the Hamiltonian is Hermitian if H equals H dagger. And for PT-symmetric quantum mechanics, we just say that that given the operators P and T, then there's a positive definite eta such that H is equal to eta inverse H dagger eta. That's the new definition of Hermitian. And then if we don't change the inner product, eta is then identity. So then H equals H dagger. So that's the definition of hermiticity. Okay, now I want to get a little bit more mathematical, and I need to because we're going to we need to be very careful with a change of inner product because at the Hilbert-space level, it's too confusing. So at this point, I want to tell you about Cstar algebra. Now, Cstar algebra came about in the 1940s and 50s, and Cstar algebra was motivated by the question of whether quantum mechanics was fully general. So, people wanted to find a way to generalize quantum mechanics, and they did so by turning it into an abstract algebra. And the abstract algebra takes operators, which are observables. And so essentially Cstar algebra just says, let's take observables. Observables are just self-adjoint operations. The star operation for a Cstar algebra, mathematicians write star, physicists write dagger. So the star operation is just dagger in mathematics language. And so Cstar algebra just says they're observables. And then if you think about commutators between observables, that's all the Cstar algebra does. It just says, you have some sort of algebra, comes out of commutators of observables, and you have a way of taking adjoints. Then with a Cstar algebra, you need states. And states are represented usually by little omega. And those are linear functionals on the algebra. So it just says that if you take a state and an observable and take the let the state act on the observable as a linear functional, that will give you a number, and that number is essentially what the overlap is. So we're formalizing that overlap. And then a state has to satisfy two properties. The state has to map A dagger A, mathematicians write A star A, to be non-negative, and the state acting on the identity operator. Now, in a lot of textbooks, it says equal to 1, but I argue that for this, PT symmetry and inner product change, we have to allow less than or equal to 1. And the less than or equal to 1 here is saying that the norm can decrease. So if an inner product changes, norm can change. If you make this an equal sign, like a lot of textbooks do, then you'd be forbidden from changing the inner product. So that's why I'm emphasizing this. In order to allow a change of inner product, this is a key point, that making this less than or equal to 1 is not what it says generally in textbooks. So I'm modifying quantum mechanics here, and I want you to have your eyes open to that. Okay, now the next thing that I want to mention to you is what's known as the GNS, or Gelfand-Neymark-Siegel construction. We take this for granted as quantum physicists. So typically in quantum physics, okay, so you can ask the question, is given a Hilbert space, how do you write the operators? And the way that you think about writing operators, you'd say, well, the Hilbert space has like ket psi. So this Hilbert space could be the set of all vectors that it can be written as ket psi. When you make an operator, you have a ket and then a bra. And the idea of what's called a lift, and I'll use the term lift, when we lift Hilbert space to the operators, we have to have the ability of taking ket of the ket and the bra. But how do we construct the bra? The answer is that we use the inner product. So if I'm going to change, this is why I need to get formal. If I'm going to change the inner product, then that means even how we go from a ket to a bra becomes non-trivial. So the mathematical relation, you wake up in the morning with one inner product, you go to sleep with another, then if you wrote on a piece of paper your ket psi and your bra, in the morning, your bra psi is just turn the column to a row and take complex conjugative elements. But at night, it's no longer the case. That bra psi is a different way of writing it. So that's why we have to be very careful. And the idea that we can somehow do that lift to go from states to operators is what the Gelfand-Neymark-Siegel construction does. So if we're going to relax the inner product condition, we have to make sure that we're still consistent with the Gelfand-Neymark-Siegel construction. So here's some notation that will become important later. So first of all, we have our A, that was the Cstar algebra. And so we have some observable, it could be a number operator thing, or it could be spin or whatever. You take some observable. Then pi is the mapping from the symbol in the algebra to the operator on Hilbert space. Okay, now often in quantum physics, we think of them as the same thing, but they're not. The algebra is simply a bunch of symbols and how they behave, their commutators behave. Then this is a way of essentially representing it as bounded linear operators on Hilbert space. And then we have a way of mapping those to states. And so if we have an operator, we can map it under sharp pi to a state, or vice versa. So we know that we can take states and represent them by operators, and vice versa. And then we just have to make sure that our pi behaves well on the adjoint. So if we take the adjoint of A, then the operator has to be the dagger. So I'm going to use star to represent the adjoint in the Cstar algebra, and then I'll use dagger to represent the adjoint for the operator. Okay, and then a pure state, which lives in linear functionals, can be represented by the operator rho, which we normally do in quantum mechanics, and if it's pure, it's ket psi, bra psi. And so we say a state is represented by a density matrix. What we're really doing is inverting the sharp pi map. Okay, and then this is all based Gelfand-Neymark-Siegel construction. tells us how to do it. Given a Hilbert space, work your way up or work your way down. And now the next thing is that we have different representations. So this is not unique. Pi says if we take the Cstar algebra, we can represent it by an operator, but we can have different operators. So we can have pi that allows us to write the operator in one way and pi prime as another operator. And then the proof that this is Brody's work that I mentioned back here, consistency, is essentially recognizing that if you have a pi or a pi prime, two different ways to carry the algebra over to B of H, they're observationally indistinguishable. So this result here is essentially Brody's proof in one line. Okay, so I'm just trying to abstract it a bit. The papers, most of Azadeh Brody's, take a lot of work to go through, but I just find if I elevate it to a Cstar algebra description, I can simplify the proofs and then use them. Okay, so how are we going to deal with the changing inner product? You wake up in the morning with one inner product, you go to sleep at night. Well, the first rule is that that the inner product is associated with the metric operator. And the metric operator can be expressed as an element, as essentially a linear operator, the bounded linear operators on Hilbert space, such that eta is greater than 0. So it means it's a positive operator and it's self-adjoint. Then if we modify the inner product, we take Hilbert space, we don't change the vector space, but we do change the inner product, then so if we just say for simplicity, the inner product in the morning is the trivial one, then in the evening, the idea is that we want to take, instead of the inner product mapping ket phi and ket psi to bra phi ket psi, we slip an eta inside. So a changed inner product is equivalent to modifying the inner product by slipping a metric operator in the middle. Once we do that, and we use the Gelfand-Neymark-Siegel construction, so we're back using that construction. Once we modify Hilbert space and we're careful with that construction, then everything just falls into place. So the idea is that we represent the algebra on the Hilbert space. So these are the ket psis. The bra phi, we have to figure out how to do it. So the idea is that we have a modified pi, and it says take an element of an observable A, and then map it to pi of A, that's the operator for it, and sandwich it between e to the minus a half on the left and e to the half on the right. Okay, and that goes back to, where did I do that? Yeah, here. So that's essentially built on this rule. Sorry about this, yeah. So the operator A maps over to e to the minus a half, and then the operator in the trivial inner product, and then e to the half. And so this can be regarded as a change in representation. Just says that if you take an element of the Cstar algebra and you write it as an operator, you just change representation. And the definition of this change is as follows. We just write down that, if you take any ket psi in the Hilbert space and the inner product, you don't change the ket psi, but you do change your inner product, which is the sandwiching the eta in the middle. Okay, now in this case, I'm using a diagram. So I think it's easier to follow if I have this diagram. And let's go through this. So here, the idea is that the Hilbert space maps under the inner product change to H sub eta. So in the morning you have H, in the evening you have H sub eta, and I sub eta does the map. The lift was the one that turns Hilbert space into operators, right? That's the, you have to be able to make the bras as well as the kets. So in the morning when you do your lift, it's trivial. A ket psi, that's a column vector, becomes the row vector of complex conjugates. In the evening, your lift is different because you need to build in this bra phi eta. So in the evening, your lift takes the kets and leaves them the same, but it modifies the bras. And then we can write a channel that carries B of H to B of H eta. which I've written explicitly here. So the channel just maps operators to operators by changing an operator M to an operator M eta. And then we can do our sharp map to states. So once we do this, then we have the rule for states, and the sharp pi eta lifts it in the evening. And the effect is that we have a channel. So states map to states under a channel. This means that if the inner product changes between morning and evening, then that would correspond to a completely positive channel that's not trace preserving necessarily. So it's a trace non-increasing channel. And so it's a very important point here. By constructing that mathematical structure, is that inner product change, provided the inner product corresponds to a positive definite metric that conserves identity, then the inner product change is exactly equivalent to a channel that is not necessarily trace preserving. And if when we do that, we care about how it behaves on the operators, we're able to prove that this E eta tilde is just a composition of F eta followed by R eta. R eta is the change of representation. So it doesn't feel so physical. F eta, though, takes M to eta to the half M eta to the half. And this is the part that captures the change of norm. So remember what I told you about cloning. If the inner product changes, you can do perfect cloning, but only some of the time. So the sum of the time is captured in this F eta. So we do this decomposition. Oh, sorry, I didn't go through that. So then the R eta is just a change of representation, which we can see is not physical. And the F eta is the important part. And then because that behaves as a channel, we're able then in principle to do process tomography to obtain eta. And this is where our experimental collaborations come in. We can then design a way of changing the inner product, do process tomography on it, and then we're also doing a unitary map in a higher dimensional Hilbert space to just confirm. So let me explain that. Okay, so how are we going to implement it? Well, first of all, the idea here, if there's an inner product change, we can write a channel for it. And again, channel, the word channel usually is trace preserving, and I'm relaxing it to trace non-increasing, and we could do process tomography. Now I'm going to go into how we can simulate this by a unitary map. So the way we do this is that we take, and I'm writing this as a PT-symmetric transformation, which I explained is equivalent to inner product change. And so now we take a density matrix, map it to a new density matrix. The new density matrix is given as follows. We take the old density matrix, and then we take a unitary operator, so an isometry in Hilbert space, and we conjugate, but we have to multiply it by a kappa. And that kappa is greater than 0, and here you can see the upper bound. Kappa is kappa captures that change of norm. So a change of inner product necessarily results to a drop in norm. And the UPT is e to the minus I HPT over H bar. And that Hamiltonian is not self-adjoint in the usual sense. It's self-adjoint in the sense that eta comes into play. Okay, and when I say that, this is right here. So HPT is self-adjoint in the sense of most of Azade's work. H dagger PT is eta HPT eta inverse, and then that guarantees that that operator is Hermitian under that definition. UPT is not unitary in the usual sense. Some people use the term, I think most of Azade use it, this is sometimes called quasi-Hermitian. And then the UPT is then quasi-unitary. And so the idea is that UPT is then given by the root kappa term, that's what drops the norm. The inner product change, that was the inner product change under eta, and the inner product change under eta inverse. So what's happening is we're saying that the quasi-unitary operator generated by this quasi-Hermitian H is equivalent to changing the inner product then applying a unitary operator, then changing the inner product back, and then multiplying by root kappa, which is 1 over the norm of that eta inverse operator. And then this corresponds to the drop in norm. And then you can see here the sequence in this diagram. So here's this kep psi. You wake up in the morning, you have a state kep psi. During the day, the inner product changes. That's the I eta. Then you get the same psi back. So your ket doesn't change under a change of inner product. But the change of inner product will change the rule of how to turn kep psi to bra psi. Then you apply the unitary evolution, and then you apply a root kappa and then change the inner product back. And changing the inner product back brings this root kappa into play. So what's happened in the lower row is your kep psi has become the unitary map of psi, but with a root kappa that dropped the norm. And then we do the lift. So this is all the Hilbert-space picture. The lift takes us to the operator picture. So if we represent kep psi by a state rho, then the effective inner product change, even though this doesn't change kep psi, with operators, it changes the bra. So E eta takes rho and maps it to rho eta. Then we go through the U tilde PT, which is a unitary map of rho. We get UPT rho, UPT dagger eta. So the eta captures that inner product change. Then we apply, this is the inverse map. So we get E, and then the kappa eta inverse, that's the undoing the inner product change. We get kappa times UPT rho, UPT dagger. And so the idea is that in a sense, this final operation here, this eta inverse, is saying, you got up in the morning with one inner product, before you go to bed, it's a different inner product, but you somehow have to tell yourself what you got. So if you wake up in the morning with one inner product, you go to sleep with a different inner product, and then the next morning it's back to the original inner product, you're essentially going back to the start to be able to relate your result under the original conditions. That's what this is doing. It's saying you go to bed, then when you wake up, you've got the original inner product back. That's what this operation does. And then we see a change of norm and this unitary transformation. And so the way that the experiment works, so what we're working on experimentally, is a qutrit simulation of that inner product change. And so now, because there's a channel, there's something from Cstar algebra known as Stein-Spring dilation. And Stein-Spring dilation says that any channel that you want to implement with a Hilbert space of dimension d, you can always find a way to convert it to a unitary map on dimension d cubed. So no greater than d cubed. So if you take a qubit, you change the inner product, then you know that in 8 dimensions, you could simulate it with a unitary map. But in fact, for our stuff, we only need one. Need to add one. So it's surprisingly efficient to do a unitary simulation. How we do it here is, so in this case, we're saying now consider a qubit and inner product change. So a qubit is a 2x2 matrix. We embed it in a 3x3 matrix. So rho is a 2x2. These two zeros are 2 component. And then, so this is a 3x3 matrix. And the way you would do it experimentally is you'd say, well, take a 2-level system. Now I'll change it to a 3-level system, but all the population will be in the first 2 levels. Then when we apply the unitary map, we need that F eta, just to remind you, that was that decomposition here. So the R eta is a change of representation. F eta is the important part. So we then apply the F eta of rho that we calculate from our inner product change. And then we project, when we do this, we take our unitary map. It gives us the F eta of rho on the 2-level system and stuff for the 3rd level. So this would be, the bottom one is the population of the 3rd level. This is coherence between the 3rd level and the first 2. But then we project back to the 2-level system. And so by just not measuring the 3rd level, we're able to then get exactly the result for the inner product change. And so we've devised the protocol and essentially the way the experiment, when we do have it ready, will work is that we first do the inner product change under the channel. We do process tomography to explain how this two-level system changes under the channel. And then when we embed it in the three-level system and do the unitary transformation, we confirm that the qutrit simulation gives, after projection, give the same answers as the channel. So the if it's done honestly, then the honest agent. So if we confirm that the qutrit simulation is correct, provided that the fidelity of the state is, and then there's a condition based on eigenvalues, and the lambdas are just eigenvalues of the metric operator. So I'm not going through the details there. That will come out more when we have an experiment, but it's kind of giving you the flavor of what's going on. And so the advantage of what we're doing is we discovered that all you need is a qutrit to be able to do a unitary simulation of inner product change. And we've extended that to general d-dimensional systems, which I won't go into here, but I'm giving you an example with a qubit, but it could have been a higher level system, and we have a generalization of that. And then this is my final slide. So as the final slide, this is just the take-home message. So first of all, inner product change is consistent with quantum mechanics. That's what I'm showing you here. Second, that inner product change is just equivalent to a quantum operation followed by a change of representation. That was this inner product change followed by a change of representation. And it can be observed and estimated. And so when I say it's observable or operational, it means that we could do process tomography to tell whether the inner product were changing. We can, because of the equivalence with PT-symmetric dynamics, we can use this inner product change to simulate PT-symmetric dynamics in that way. And finally, PT-symmetric qubit systems can be simulated on just a single qutrit, which makes it accessible experimentally. So that's the end of my talk. Thank you.
Yeah, thank you very much, Barry, for a fascinating talk. Thank you very much. And we still have a little bit of time for questions. So I would like to encourage the participants to ask questions. And maybe we can start by asking our panelists, because while you were talking, Barry, several more representatives of Africa joined us on the panel. And maybe we can start by giving them the opportunity to ask a question, because they can do it orally, whereas the participants can use the Q&A, or maybe they can raise their hand and we can give them the right to speak as well. I don't know, is there anyone in the panel that would like to ask a question to Barry? I think there was a little bit of, I think Girish. Girish, please unmute yourself and you're welcome to ask your question. Girish is the representative of Mauritius. Yeah.
Hello, can you hear me?
Yes, yes, we can hear you, Girish. Good afternoon.
Okay, thank you. Great talk. I wonder what, if any, could be done experimentally to, apply to whatever you have been talking about. Thank you.
Well, yeah. So experimentally, this is what we're doing. We're working with a group that does superconducting qubits, and so experimentally we do two things, and so the results aren't complete yet, but they should be complete soon. We take a qubit, and then we write down what the inner product change would be, represented by the metric operator. And then we design a channel, and then we just use open system quantum dynamics acting on that superconducting qubit two-level system to change it. Then we take the same system. So it turns out superconducting qubits aren't really two-level systems. So then we work on a unitary map, so quantum gates on a qutrit, a three-level system, to map it according to that unitary picture for what goes on, and then we get a result, and then we prove that they're the same. And so experimentally, that's how this works, that you can say the inner product changes in some way. Then you calculate two things. You calculate, first of all, the channel, and second of all, the unitary transformation of the higher level system, and then experimentally confirm, check if they're the same or not. And then that's a simulation of what goes on. And the reason for doing the experiment is because it's weird that the inner product changes, and it's nice to see experimentally what an inner product change would do to quantum mechanics. Oh, and I'll mention too, this work I'm doing at the moment. There were papers that essentially said PT-symmetric quantum mechanics would allow enhancing entanglement. So there were claims about entanglement. So that'll be future work that I have coming out. But to do entanglement, we need tensor product structure done properly. And so the question of whether entanglement can be modified by an inner product is an interesting question. I know the answer, but I won't say it here. It'll be out future.
We will invite you again next year, Ben.
Yeah, exactly. I see more hands up.
Yeah. Murad, please, you're welcome to unmute yourself and ask your question.
Yes.
There is a bit of feedback.
Thank you very much, Barry, for this wonderful talk. Highly appreciated here by our colleagues and students at the University of Tunis Al Manar, Tunisia. So on behalf of our Quantum Network and my colleague Siem Jaziri, we are very grateful to you for this nice piece of science. I may have a couple of questions about your talk. The first one would be about the time scale. So you use this picture of the daytime when you say that this drift or this variation with time of the inner product happens, you say, when you wake up in the morning and then in the evening. But what would be, according to you, realistic time scale if an experiment related to this phenomenon is implemented? So this is my first question.
Okay. So although I say you wake up in the morning and go to sleep and the inner product changed, there's no time built into our formalism. It could be done in a microsecond. It could be the age of the universe. So, and I don't have any physical reason why the inner product would change. So there's no physics giving a time scale. This is more about saying it's allowed to change. Yeah. So at this moment, I don't have any motivation for it that would allow us to know how fast it would.
Okay, thank you. So maybe a second question, if you allow me. You said that this change in the inner product may affect the cloning. So we can in some way bypass the non-cloning theorem. Yes. So can we imagine any implementation of I don't know, some teleportation algorithm based on that?
Yes. Okay, exactly. So first of all, with the cloning, as I said, the inner product change would can allow cloning. And then in quantum cloning, you can't do perfect quantum cloning, but there are two branches of the literature. One branch of the literature considers imperfect cloning. So it just says, well, you can't clone perfectly, but you can clone imperfectly, and there's a limit. And the second branch of the literature says you can clone perfectly some of the time, and the rest of the time you get garbage. And so our protocol is equivalent to the second, that the inner product change is exactly equivalent to non-deterministic cloning, where sometimes it works and other times it gives garbage. Then you can start asking the question, as you just did, Murad, is what happens to other protocols like teleportation? Now, teleportation requires entanglement. So, you have Alice and Bob and Charlie, as I like to think about it. Charlie sends an unknown state to Alice, and then Alice sends it to Alice does the joint measurement of the state Charlie sent her with her share of an entangled state. And then Bob gets instructions from Alice and modifies his share of the entangled state. And as I mentioned, nothing I did so far tells you about entanglement, because to do entanglement, we need tensor product structure. And the tensor product is requires more care. So I'm working on that at the moment. We're near finished. But your question about quantum teleportation is really good, because what would an inner product change do to entanglement? So I'll come back with an answer. As Francesco said, you know, next year I'll come back and tell you the answer.
Thank you very much.
Thank you, Barry. There is another question from the audience, and I'm giving M. Weicht, I'm not sure who that is, the right to speak. So please unmute yourself, and you're welcome to ask your question.
Thank you very much for allowing me to ask my question. And also, I found this talk very, very interesting. One question, I gathered somewhere that you change the Hilbert space, then it appears to be like it's that the two Hilbert spaces are unitarily equivalent. I think I saw it somewhere on one of your slides. So is it true then that when you change your Hilbert space, then with the inner product, then it's actually unitary equivalence going on, because your Cstar algebra must be equivalent, let's say, to your algebra of bounded operators under unitary equivalence. And then if that's the case, then if you work only abstractly in the Cstar algebra context, then is the change in Hilbert space actually hidden in disguise when you change the state?
Okay, so I think I understand what you're asking. So I put down here at the bottom, it says different representations. So
right, that's what I was thinking, yes.
Yeah, so the idea is that, you know, that the pi and the pi prime can be just related to two different inner products, and they're observationally indistinguishable because they're just different representations. So the idea is that the change of inner product doesn't do anything to the space of operators. The point is that when you start doing the adjoint, so I wrote here the representation then of the adjoint of an operator is then the usual dagger operation on that representation. That's where things get tricky. And so I'll just find it. Okay, that's the inner product change. Like you said, the Hilbert space, the cap size don't change, but the point is here. So what happens is the Hilbert space change of inner product causes the operators to go through a kind of a channel, a trace non-increasing version of a channel. And then this is a composition of the F eta with the R eta. So operators under F eta then get essentially rescaled. There's a change of basis that is not really physical, but the etas, you can think of as you know, if it's a qubit, it's a 2x2 matrix, it has eigenvalues, and it rescales M by those eigenvalues. So the question you're asking about where things are manifested, the easier language is to say the kets don't change, the bras change. By changing the bras and not the kets, the operators change in this way. And then the states change through this sharp map. So, you know, if you're basically, like if you take a density matrix as an operator representation of a state, if your density matrix changes by multiplying by eta, then your states, which are linear functionals, change. So bottom line, all the subtlety is in turning kets into bras.
Okay, thank you very much.
Thank you. And we have, Barry, we have two more questions. One by Amira, and Amira just gave you the right to speak, so you're welcome to ask your question in person.
Oh, thanks, Prof. Mine is very silly because it's probably just me not understanding the math, but just while you're on this slide, you know, why is the mapping, I was just wondering why the mapping M there, the operator is like this eta to a half times M eta to a half, when everywhere else the mapping seems to be defined as like eta to the minus a half.
Okay, yes, so you're saying, oh, you think it might be a typo, is that it?
Yeah, exactly. I was just wondering if there's like a reason or if it's just a stupid minor thing. Yeah.
So yeah, e to the half m e to the half, that's the one you're asking, right?
Yes.
Yeah.
Okay, that just comes, okay, so I'd have to go through the math, but what's happening here is the eta tilde just multiplies an eta on the right. And then what happens is we write that as a composition. And so the essentially mathematically, the change of representation that kind of absorbs a non-physical property, it's just a change of basis, is enough that we're able to write the f eta in this way. So
Okay.
we're under a change of, I mean, maybe one way to look at it, if you do a trace, there's a cyclic property. So, that if you thought about, like, it's kind of like breaking eta up. So there's a square root of eta on the left and the right is allowed to happen under the change of representation. And in a way, it's because every physical quantity just comes out of a trace of an operator in a state, if that helps. But
Gotcha,
we'd have
yeah.
to go through all the math to see it. And I don't have slides
Yes,
prepared.
no,
to do
sorry.
it.
It's a very minor question. Okay, cool. Thank you.
Yeah.
Thank you. And Barry, we have one last question by Isaac, and I gave Isaac also the right to express his question verbally. So Isaac, please, if you unmute yourself, you're welcome to ask your question.
Hi, Professor. Thanks for the wonderful talk. So my question is related to, because I mean, essentially, you just need this f eta. You need to do a process tomography on f eta to get how your operators evolve and the inner product changes. Now, the process tomography itself can be time consuming, and you need inner product measurements to also get what f eta is. What if the inner products also evolve when you do the process tomography? Will this still apply?
Yeah, interesting point. Okay. Yeah. So what I said here is the bottom is f eta can be estimated by process tomography to obtain eta. But the way I set up the problem, as you say, Isaac, is I said, well, you wake up in the morning with one inner product and you go to sleep with another one. So you're now asking the question, you're saying, well, what if it just doesn't stop changing? That's your question, right? And
yeah, precisely.
Yeah, and that's another. Okay, so I mentioned before, with entanglement and the quantum teleportation question, that it's very subtle because you have to bring tensor product into the story, and I haven't done that yet. Your question is actually related to something else that's important, and it's a composability one. So it just says, if you think of the inner product changing, and then the inner product changes again, and it keeps changing, can you compose those so it's still an inner product change? And then you can even think of a continuous time version. You could say, let the inner product change just be a continuous function of time, as another example. And so the question you're asking is really related to the following, like the following deep question I would say is, what if the whole story has inner product change that is just dynamically changing always? And so my intuition, of course, is that, if we did tomography and we knew how it's changing, we would just plug in the math. So, every measurement, you would just keep updating by the inner product change. But the truth is that we haven't yet got a mathematical result that allows us, A, to compose inner product changes. I don't think it's hard, but we haven't done that. And B, whether an inner product change can be decomposed into a composition of inner product changes over shorter time intervals. So essentially, we have to do a calculus of it. So the answer to your question, Isaac, is it hasn't been done. So what you're asking is currently an open problem that needs to be addressed, in my view, formally in terms of composability and decomposability of inner product change.
Thank you. Thank you very much, Barry, for answering this question. And a little bit in the same spirit of the question of Isaac, can I ask a question, Barry? And then I think we let you go. Yeah. If you think of the kind of the path integral approach of quantum mechanics, is it thinkable to have a scenario where the scalar product can change for each path? Yeah. Would that somehow fit in your in your scheme? or generalization would be required to do that? Because that could also lead to interesting consequences.
Yeah, exactly. So, I mean, first of all, it's very subtle, Francesco, because
I can imagine.
As you know, the path integral approach is not exactly mathematically equivalent, right? That you know, there's right. So the second thing is, like I mentioned, tensor product, right? So, you know, if you start thinking about different paths, how do you do it? Like, do you make how do you lift it all to that path integral
I don't know.
way? And another way of asking the question, like even with path integrals, instead of waking up in the morning and going to sleep with the inner product change, you could just say, well, you know, Francesco, if you're in South Africa and I'm in Australia at the moment, and I send it to you, and South Africa happens to have a different inner product than Australia, and then you send it back, and then you start asking, well, you know, so if I send to you and you send it back, that's a different path than if I never sent it to you at all. And so the idea of going from a time dependent to a spatially dependent picture is not solved yet. And, you know, to do it all in a way that's consistent, relativistic and everything is that we should be saying, what if the inner product just changes in an arbitrary space-time dependent way? And then the path integral stuff becomes a useful way to think about it. Not addressed.
Okay. No, that's very interesting. So you will be busy for a while.
Yeah, I'm looking for ways to keep busy, and this is doing it.
Yeah, no, that's fantastic. Thank you very much. Okay, so I think this brings our colloquium in celebration of World Quantum Day to an end. So Barry, thank you so much for being with us. I know that for you it's almost time to go to bed. Yeah, it's time for the late scalar product, not the morning one. Yeah. So we wish you a good night, and thank you very much for being with us this afternoon and for sharing this really very interesting talk with us, and that we will keep following, because there are probably many interesting consequences that we're probably not even aware of at the moment. Yeah? I would like to thank also all the participants and all the panelists that represent the various African countries. And maybe if I could ask the panelists to quickly switch on their video, we could quickly take a screenshot for posterity. Yeah. So if you don't mind quickly switching on your video, I will quickly take a screenshot. Sorry, I'm almost there. Just a second. And I don't know if Makamiza and Yasin, can you quickly switch on your videos? Okay, I don't know. Let's wait a second. Okay, maybe it doesn't work. Okay, I take we can Photoshop them inside again later. So then again, thank you very much, everyone. Barry, if you agree, we will post the talk on our YouTube channel. Is that okay with you?
Mm-hmm.
Perfect.
Yep,
here they come. So we need to take the screenshot again. Makamiza, if you're there, can you switch on your video as well? Ah, fantastic. Okay, then a big smile, and here we go. Perfect. Thank you very much. So I will share this with you later. Yeah. So thank you very much, everyone. Don't forget that at 3:30 we have another World Quantum Day event, a panel discussion with Sir Peter Knight, who kindly joined us during the talk as well. So you find the link on the NITEX website if you haven't registered yet. Yeah. So thank you very much, everyone. Happy World Quantum Day, and we will all stay in touch. Thank you very much. All the best. Thank you.
Thank you. Thank you.
Thank you.